can say, let's say you have a battery that's not 120, some random battery, let's say 50 volts. Then you connect it to a light bulb. Let's see. Let's say 20-watt light bulb. So I could say, okay, in this circuit, which of the light bulbs is the brightest? Which of the light bulbs is the dimmest? The way that I have it connected. Which one is brightest? And dimmest. And then what's the actual power of each one? In other words, this is only their rating. They're rated at that, but that doesn't mean they'll be fully lit. You know, so they will not be fully lit because they're not connected to a 120 volt source, and plus there's a bunch of them too. So which one is brightest and dimmest, and what is the actual power? What is the actual power output of each light bulb? What is the actual power? Actually, we can say, it's better to word it this way. What is the actual power consumed by each light bulb? Consumed by each light bulb. The reason that I word it that way is because these numbers are a measure of how much power the light bulb is consuming from your house, electricity. They're not really a measure of the light output of that light bulb. The light output is measured in something like lumens, 1600 lumens, or let's say something like that. So when we're saying I'm buying an 80-watt light bulb, doesn't mean it's producing 80 watts of power. It means that it's consuming 80 watts of electrical energy from my house, and I'm going to have to pay for that, do you see? So we're usually saying how much it's consuming, but of course, the more it's consuming, generally it should be brighter too. It should give more. So a 40-watt light bulb should give something like 800 lumens, let's say. 60-watt light bulb might give you 1,000 lumens. Yes. So, but usually we're saying how much the light bulbs are consuming. Okay, so how do we do this? Well, we change this into an equivalent resistor circuit. So we calculate the resistance of each one, and then we make it into a resistor circuit. So how do we calculate the resistance of each one? This equation, right? P is V squared over R. R is V squared over P. And then so 20-watt light bulb's internal resistance is what? 120 squared over 20. So remember, the 20 watt is its rating when it's running across a 120 volt source by itself, you see. So then that's going to be 144.00 over 20. That's going to be 720. Okay, so this one has 720 ohms. Right, and then the 60 we already know from the previous example. The 60 is what was it? 240, right? Yeah. And the 40 would be okay, if it's twice the power of that, then it's going to be half the resistance, right? 40, yeah, 40, it's going to be 360. So this is a 360 ohm resistor. And then the 80 is going to be, well, the 80 is going to be twice that. So it's going to be half of that. So 180. So these are their resistance. Those are the resistance of their filaments, right? Then you change this into a series. Okay, so now you could say these two are in series. Well, it's kind of like the circuit that we did yesterday with the simulation, right? But here we're focusing not so much on voltage, but our eventual goal is to find out, okay, which one's the more power consumed, and therefore which one's the brightest. You see, that's kind of our focus in this kind of a problem. Okay, so when you add that, you get what? 600? 600, and then here you get 180. Okay, and then you do the parallel. 1 over r prime is going to be 1 over 180 plus 1 over 600. And then 1 over r prime is going to be 600 plus 180 over 180 times 600. And r prime is going to be 6 times 18. It's going to be 48, 46, 108, 0, 0, 0, 3 zeros divided by 780. And then the last zero cancels. Okay, so then 108, 108, 0, 0 divided by 78. 138.461538 ohms. Okay, and then that one gets added to this guy, right? So this is 720, 138.46. Then add them in series, and then just add 720 to this, right? In series, plus 720. Okay, your total resistance is 858.4615. Then you can say, okay, now let's calculate what the current there is. 50 over this number. So invert this number, multiply by 50. 0.0582437 amps. And then those two will have the same amps. I'll just put this as, I'll call it I1. I'll say I1, I1. Then I'll say, okay, then the voltage of this guy is going to be this number times 138. So times 138.461538. Okay, so then that's going to be 8.0645 volts. Right, and then that's going to be the same voltage as these guys, 8.0645 volts. 8.0645 volts. Okay, so then I go back. So then I already know the voltage of that, which is the voltage of that. So then I'm going to calculate the current of this. Current going through here. So then I'm going to say 600 by, no, the voltage divided by 600. Divided by 600. Okay, so then this is going to be 0.01344 amps. Okay, and then I could find the power of it. So since I'm concerned mainly with power, all I need is the relevant information. Okay, so now what's the actual power output of this one? Okay, so then the power output of this one, I know it's, I know the current. I never actually calculated the voltage of this, but if I know the current, I could just do the power of this is I squared R. So if I didn't calculate explicitly its voltage, then I can just do the current squared. So the current was this guy, right, through here. So 0.0582437, 0.0582437 squared times the resistance was 720. 0.0582437 times 720. Oh, okay. So this is it. Wait. 0.0582437 squared times 720. Oh, okay. 2.442 watts. Well, so it's going to be barely visible, the watt. That's how much power it's going to consume, right? Therefore, it's going to not light up that much. Well, then the same thing with this. I know the current, so then I'm just going to do the current squared times 240. Current squared times 360, right? That's all I'm going to do for that guy. So then I'm just going to do 0.0 0.01344 squared times 240. Ooh, this is barely visible. 0.0434 watts. And then this guy is going to be, well, you can divide by 240 and multiply by 360. Divide by 240, multiply by 360. It's going to be 0.065 watts. That's weird. The 40-watt light bulb is going to consume more power and therefore shine brighter than the 60-watt light bulb. You see that? So this is going to be shine brighter than this guy. This one's going to be a lot brighter than either one. So okay, how about the 80? That's actually the brightest, the best rated one. It's got the least resistance. So let's see how bright that will be. How do we do that one? Well, I believe I know the voltage, right? Yeah, right here. I already know the voltage of this guy. And I never found the current, but I don't care. So I could just do, if I know the voltage, I could do what? The voltage squared over R. So I'm either doing voltage squared over R or I'm doing I squared R. I never did VI for the resistors because I either didn't know their I or didn't know their V. Right, and then so the voltage is going to be 8.0645 divided by the resistance of this, which is 180. But then square the voltage, right? So take the voltage, square it, divided by 180. Let's see what that comes out. So this one is 0.3613 watts. So it's brighter than these two, but not as bright as that. Kind of like this. Now, how do I know if I did it right? Remember, with capacitors, we added their energies, and it would give you the energy of the produced by the battery. Okay, with this, we can add up their powers, and it should give you the power produced by the battery. So how do we calculate the power produced by the battery? You just do voltage of battery times the current running through the battery, right? So for the battery, you use VI. You can't use I squared R or V squared over R. So then you just have like that. Okay, so then you're going to have what, 50 times that current here that was running through the circuit. So this is the total current, right? That's running through the battery. So then 50 times 0.058. So I'm just going to use the full number here. 0.058 2437 times 50. So the total power produced by the battery, 2.912185 watts. 2.912185 watts. So now let's add up all their powers, right? And let's see if we get 2.912. So 2.442. When you're adding powers, it doesn't matter whether they're series or parallel. You just straight up add them. So then this plus 0.0434 plus 0.065 plus 0.3613. 2.9117. There's still rounding error. It's not quite what I have here, even though I use that many decimals, huh? So I'm getting 2.9117, but yeah, it's rounding error pretty much. Yeah, that's pretty close. So you see the power is conserved. Whatever the battery is producing, the resistors and the light bulbs are consuming. So now the conclusion as to which one's the brightest. Which one is the brightest? So of course this is the brightest. And the dimmest is this one. This is the brightest, this is the dimmest. Now the question is, could we have answered that without necessarily, let's say you're just given something like this, could you get so good at it where you can answer that without necessarily doing all this calculation? You see? So what's the logic? How can we argue that this should be the brightest and maybe this is the dimmest? Let's see. I guess you could kind of argue, okay, look, if this is a 80 watt, it's got a very low resistance. Its resistance is 180, but you don't necessarily need to know that it's even 180. The higher the wattage, the less resistance that it has. So here you have 60 watt, which already has a larger resistance than this. And then here you have a 40 watt, which is already a larger resistance than that. Then they're in series, so the net resistance of this is going to be more, right, than the resistance there. So now we know that these two are in parallel, right? So what about them is the same when they're parallel? Their voltages, right? So then the power consumed by this is V squared over R, And the power consumed by this is V squared over the combined R, right? So together, if we say the power consumed of both of them together is V squared over their net resistance of these two. But then these already individually are high resistance, right? So when you combine their resistance, that's even going to get larger, and they together share the same voltage as that. So it has a big resistance, but the same voltage. So the power is little. So just from that, I could argue that this guy is going to have more power than even these two combined, which it did, right? When you add this to that, it's less power than this one had. You see? So that means I could kind of argue that this has more power than these two. Then between these two, how can I argue that this is going to be dimmer? How can I argue that? They share, if they're in series, they share the same current. So then if they have the same current, who's going to have the least power? Two light bulbs that are forced to be in series together, right? They're going to have the same current. So if they have the same current, if the I is the same, the one that has the less resistance is going to have less power. You see? Now, higher rated light bulb has less resistance than a lower rated light bulb. So a 60-watt light bulb that's forced to be in series with a 40-watt cannot fully shine as bright as it's supposed to, because it's got to have the same current as that. So it's always going to be dimmer. Let's see, was it dimmer? Yeah, 0.04 versus 0.065. Right? So it's always going to be dimmer. So in other words, that this is a generality that two light bulbs that are forced to be in series, they always will share the same current, and therefore the one that has least resistance. Well, the least resistance is the higher rated light bulb. But the problem is the higher rated light bulb cannot shine that bright because the lower rating one will limit the higher rated one, you see? So we could say that as a generality, any light bulb that's forced to be in series with the higher rated one cannot actuate itself, cannot fully potentially actualize its full potential, right? Because it's limited to the same current. It's almost kind of like, you know, how some parents say, I don't want my kid going to public school because they're going to get the same education as everybody else. It's kind of poor education. I'm going to keep them in my house and do homeschooling, right? Because their argument is when they go there, they're in series with everyone, you know. They're getting the same education, so they're limited to the same resources and the same attention, so they can't actuate their potential, right? So I'm going to teach them myself, and they're going to go learn more in a shorter amount of time, which sometimes is true, you know, but then you're just missing out on that social aspect. But yeah, that smarter person, that kid that goes to a public school, sometimes is limited by the fact that everyone has to sort of go at the same pace, you see? Kind of like that, you know, not exactly, but sort of. Okay, so from there we can argue, oh, okay, so these two together, this is brighter than the combination of these two. Already we know that, and then therefore this is brighter than that. So this has got to be the dimmest one. Now, can we argue that this 20 watt is even brighter than the 80? Let's see, how would we argue that? This one is going to be, this is going to be 180. It's going to be this. Oh, okay, here's what the argument we can make. We can say together this and this, what's their net resistance? What's the net resistance of these? Well, this one's resistance is already low, right? And then when you put two resistors in parallel, their net resistance is lower than the lowest one. You see, when we put this next to that, what was the combination of the two resistances? It turned out to be 138, right? So between the 138 and the 720, who's going to be brighter? I'm just looking at purely at their resistance, right? So it's the same argument. The lower rated one has a higher resistance and dominates. And so this lower rated one, because it's in series with the combination of these two, the lower rated one dominates and is therefore brighter. For the same reason that this is brighter than that, the lower rated one is brighter than the combination of these two. Okay, from that argument, I can say this gotta be the brightest, and then therefore this is the dimmest. Yeah, you get my arguments? Okay, well, how about something like this? Maybe this isn't as obvious. Let's just change those light bulbs around. How about this? I kept the circuit the same, but just changed the location of the light bulbs. Yikes. Okay, try to do this without using any of the equations. I mean, you could look at these equations, right, to kind of guide you, but don't formally do anything. Argue with me which one is the brightest and which one is the least bright. It's going to be the similar one here, but I've moved the 20 to here. I moved the 40 to here. The 40, I moved it here. The 80, I moved it up there. And then the 20, I moved it down here. Now who's going to be the brightest? Who's going to be the dimmest? So let's rate them. Brightest, second brightest, third brightest, and then the fourth is the dimmest. So now tell me which light bulb is it? Which rated light bulb goes in here? In other words, put your rating down on the chat board. Number one is which one? Number two, let's see who agrees. Help. What was the resistance of the 80? Yes, there. Matthew says the brightest to dimmest. Matthew says 80 is the brightest. So he says this one is 80. And then he says 40 is the second one. Then 20 and 60. Okay. Any agrees there? Or any disagrees? So you're saying, again, this will dominate the circuit, huh?
10 out of 10. No. Let's see. I mean, I'm sort of inclined to agree with Matt on this one.
Huh?
No, I'm saying I'm inclined to agree with Matt on this one.
Yeah, okay, you're agreeing with that? 80, 40, 20. So you're saying it doesn't matter if the 20 is there and the 80 is there, this guy over here will always dominate.
Well, yeah, because I was thinking on the, just as a matter of like how much current is flowing through, right? You have the most current flowing through that guy.
Through that one. But then how about the fact that its resistance is low? Because when we had the 20 over there, its resistance was 720 over here. You see what I mean?
Right.
It's a bit tricky. Ultimate way to go about it is quickly solve, let's see here. Let's see, 180. What's the combination here? 960.
Yeah, because thankfully all the calculations are pretty quick, so it's not that bad to do anyway.
360. This is the only tricky, it's more work. 1 over r prime. But maybe we don't necessarily have to do the whole exact number. We can maybe ballpark it. We could say this combined will always give me a number less than either one. You know, so maybe I'm just gonna guess. It might have to do with the exact number, but I'm saying we might not need the exact number. So we're saying r prime is going to be approximately less than either one. So let's say it's 300. Oh, but it might matter what it actually is, right? Because we're trying to compare to the 180. Oh, okay. You know what? Let's just get the actual number. Let's see here. I'm just going to do 1 divided by 960 plus 1 divided by 360. And then reciprocate. Oh, 261. I'm not going to go that many decimal places. So, okay, so that's larger than that. So combined, this is going to be brighter. This two are going to be brighter than that. So 180 is going to be 261. Okay, so then the total resistance is going to be, what is that, 441. Okay, now at this point, maybe we could just round it. We could say 440. So the total resistance of the circuit is approximately 440. Then we can say, okay, the current there is going to be 50 divided by 440. So then these two will share the same current, right? Okay, therefore the brightness of the 180 is going to be what? Brightness of the 180 is going to be that current squared times R. 50 over 440 squared times R. So this is approximate, but okay, so let's square this number. 50 divided by 440 squared times 180. 2.32 watts. Okay, then let's find out the voltage of this guy. If I know its current, the voltage of this guy is going to be current times resistance. So it's going to be 50 over 440 times the resistance, which I'm going to approximate as 260. .5 volts. So this guy has 29.5 volts. This guy has 29.5 volts. Okay, so then if I know the voltage of this guy, I do V squared over R. 29.5 squared over R. So squared divided by R. Oh, that was a close one. Ooh, 2.42. It's brighter. Dang it. That one was a tough one to guess. 2.42 watts. Okay. Now, between these two, we could kind of guess, right? This together, this is going to be that many watts, but then this is going to take majority of it. Okay, so the order looks like 20 is the third one. Matthew, you're correct. 60, you're correct. So between series, the lower wattage always wins, but these two are switched. That one was a close one, very close. The fact that this is 80, it has low resistance. The problem is when it's in series with a couple other light bulbs, it might lose, and it lost to the 40. Even though 40 had less current than 80, but the resistance of the 40 is more. So this guy won by just a little bit. So the answer was 4080. I don't think I could have guessed that either. I mean, I was going to guess either 80 or 40 as the brightest, but I wasn't sure either. You know, it was actually the, wait, did I write correctly? No, I didn't write correctly. This is the 40 wins, and the 80 is actually second. So this guy came second. This is actually brighter than that. That's weird. But you can kind of see, right? Because it's got a less resistance, so it lost to that one. Okay, good.